So again, hello everyone, and welcome to today's session on the challenges of deploying multilingual models in production. My name is Dmitriy, and I'm an AI and ML engineer and data scientist specializing in NLP and AI systems. A bit about my background. I completed my master's in AI at Queen Mary University of London, and I spent considerable time working with multilingual systems in real production environments. So today we're going to bridge the gap between what you read in research papers and what actually happens when you deploy these systems um, in order to serve real users. And this isn't just a theoretical talk. Everything I'll share comes from real deployment experiences. Um, okay, so let me start with a question. Type in the chat if you've ever trained a multilingual model that looked great in development but disappointed you later on in production, or if you were surprised by how differently it performed by between languages. Yeah, yeah, we've all been there. So here's the gap we're dealing with. Research papers will tell you something like MBERT achieves 85% F1 score across 104 languages. Sounds quite impressive, right? But then you deploy it, and suddenly your Russian accuracy has dropped to 67% with real user data. But like, what changed? That's exactly what we're going to explore today. Research papers, they usually test uncurated clean data sets like XNLI, VKN, or POSX. However, real production data is messier. You have typos, mixed languages, domain-specific terminology, inconsistent formatting, and just like, for example, users write things like great font for kids, but instead of great, like a normal word, you have GR8 as a number and 4 as a number, which is quite confusing for a model because it has never seen that kind of text. Then papers also talk about cross-lingual transfer, but they don't mention that English to German transfer works way better than English to Thai. Academic metrics like F1 and accuracy, they just don't capture production concerns like latency, cost, and maintainability. And the biggest mistake I see that teams make is they assume that if a model works well on benchmark data sets, that it definitely will work well on their data. But unfortunately, benchmarks are clean and your data isn't. Here's what we'll cover in the next 45 minutes or so. First, we'll dive into language specific performance gaps, like why models favor some language over others. Then we'll tackle data quality challenges like mixed content, code switching, and encoding issues. After that, production constraints, latency, costs, infrastructure, reality checks. And finally, we'll wrap up with the best practices and practical strategies that actually work, that are actually tested. And finally, we'll have a Q&A session. And for those who are currently working with or planning to deploy multilingual models, this should be directly relevant. And for those who aren't yet, you'll learn why this is harder than it looks and what to prepare for when you actually do. Let's start with a fundamental truth. Obviously, not all languages are created equal in the eyes of multilingual models. Look at this chart on the left, showing training data size versus downstream task performance. The pattern here is quite clear and consistent. High resource languages like English, Spanish, German, and French, they have billions of tokens in the training data, and they typically achieve 80 to 90% accuracy on downstream tasks. Then you have mid-resource languages like Russian, Turkish, and Vietnamese with millions of tokens. And you're looking at about 70 to 80% accuracy, which is a noticeable drop. And then you have low resource languages like Kazakh, Uzbek, and Khmer with limited data. And performance is highly variable and often between 50 and 65% on downstream tasks. But why does it happen? Models like MBERT, they were trained on Wikipedia data, and Wikipedia size varies hugely by language. Like for English, you have over 6 million Wikipedia articles, but for Kazakh Wikipedia, only 300,000. And this creates a fundamental imbalance that never fully disappears. So when I was fine-tuning XLM Roberta for product classification, I found that English product titles achieve 89% accuracy. German was close at 86. Russian dropped to 78, and Kazakh was 64, which is barely usable. I had the same task, same amount of fine-tuning data per language, so the conditions were basically the same. The only difference was how well the model works with the specific language. So the key takeaway we have here is don't assume multilingual means equal performance across languages, because it simply doesn't. So now let's look at the main models you'll encounter and when to use each one. MBERT, which stands for Multilingual Bird, is the original multilingual model. It supports 104 languages with 110 million parameters, and it's still quite good for many tasks. The main advantages are its smaller size and faster inference. The downside is of course, it's an older architecture from 2018, and its vocabulary tokenization is not that efficient for non-latent scripts. We will see that a bit later with examples. So use it when you're cost sensitive, you need fast inference, and your languages are mostly high resource. Then we have XLM Roberta, short XLMR. And it's the powerhouse. It's my go-to for accuracy critical tasks because it has a better architecture and it was trained on Common Crawl, which is way more diverse than Wikipedia and achieves state-of-the-art performance. The downside is it's 2.5 times larger than MBERT. The base model is 270 million parameters and the large one is 550 million. And that comes down to slower inference and higher infrastructure costs. Use cases are when accuracy is paramount and you have GPU resources. Then we have MT5. It is for generation tasks, translation, summarization, question answering, and it can obviously generate text, not just classify. But it's quite massive. It's up to 13 billion parameters for best performance. It's expensive to deploy, and most of the times it's an overkill for classification tasks. And you also have language-specific models like Camembert for French or Rubert for Russian, and often they give you a slight boost to performance, like 3 to 5%, than multilingual models for that single language. But there is a downside that there is no cross-lingual transfer, and you must maintain multiple models, which requires more human resources. And so, when choosing, you can ask yourself 3 questions: how many languages do I actually need? What's my latency budget? What's my accuracy requirement? And these 3 questions should guide your decision. Now for the cross-lingual transfer. It is the idea that if you fine-tune a multilingual model on English data, it will automatically work reasonably well in other languages. And this is partially true, but with massive caveats. Look at this heat map on the right. It shows transfer performance between language pairs. The diagonal is always 100% because that's training and testing on the same language, obviously, but notice how quickly performance drops as you move away from the diagonal. English to German transfer retains about 90% of English performance, which is a pretty good performance. English to Russian drops to about 75%. English to Thai around 60, and English to some lower resource languages can drop to 50 or even lower. But why does transfer even work when it does? The first reason is shared subword tokens between languages, especially those languages that use latent script. Then there are also universal concepts like product price that exist across different languages. And also the multilingual pre-training creates a shared semantic space. But why does it fail? There are script differences. Latent to Cyrillic has some shared tokens, but latent to Thai has almost none. Then there are cultural concepts that don't translate. For example, Black Friday in Western e-commerce versus Asian markets. Then there are also word order differences. English is a subject, verb, object, and we have Japanese, which is subject, object, verb, which affects how models process context. Uh, Before this webinar, I actually ran a sentiment analysis experiment, a quick one. I trained 50,000 English reviews with 88% accuracy on English test set, and I compared that to zero shot on German, which was 82%, quite good. Then zero shot on Russian dropped to 71%, which is mediocre, and zero shot on Arabic was 58, which is basically, it's like barely better than random. So what's the key takeaway here? Like the practical implication that we can take away from here is, if you're doing zero shot cross-lingual transfer with no target language training data, you are basically, you should expect to lose 10 to 40% performance depending on language similarity. So you have to plan according for that. Let me show you now a real case study from a product classification system. This table here shows the gap between benchmark performance and production performance on a specific task. English showed minimal degradation, 91% on benchmarks, 89% in production, just 2-point drop. The main issue was domain-specific terms not in the training data. Then Spanish dropped from 88 to 83%, which is a 5-point gap. And the problem, well, different dialects. Different dialects use different terms. Computer, for example, is computadora in Mexico, but ordenador in Spain. A model trained mainly on European Spanish will obviously struggle with Latin American variants. Then we have Russian, which dropped from 84 to 72%, a 12-point gap. Then the major issue here was users mixing Cyrillic and Latin scripts all the time. And Ember treats these as completely different tokens. For example, iPhone can be both in Russian and English. These are two different words to Ember, basically. And Kaze had even worse degradation from 76 to 58% because there is even more even more mixing English and Russian words, and a lot of the times in the same sentence. So a lot of code switching. What's the key takeaway here is, don't trust your development metrics, and always test on real production data from each target market, because the gap may be surprising. Now for the tokenization biases. This is one of the most underrated problems in multilingual NLP, because tokenization determines how much actual information your model can process. Let me show you how models break text into pieces. Let's take the phrase, "I love this phone." In English with Embed, we get 4 tokens. I love this phone. Simple, right? Clean and efficient. But for Russian, the same equivalent would get split into 7 tokens. For Thai, it's 6 tokens. So we can see that non-English text uses tokens less efficiently, which means a shorter effective context. Now let's look at this visualization on the right of effective context windows. Embed and XLMR both have a 512 token limit. For English, that's approximately 512 words, so 100% capacity. For German, it's 88%, which is 450 words. For Russian, it's 74%. Thai 55%, and Chinese even lower, 51%. So in practice, that means that for product classification, an English product title plus description fits comfortably in 512 tokens. but the equivalent in Thai with exactly same length might need truncation, losing important context. So you're feeding the model less information, which directly impacts accuracy. And so how can we use it? If you're seeing, how can we use that knowledge? If you're seeing unexpectedly low performance in non-latent script languages, you can check your average token count per text, and if it's much higher than English, you can consider language-specific models, custom tokenizers, or even preprocessing to reduce token count to combat what we see here, the tokenization bias. Now the mixed language content problem. In any real production system, especially e-commerce or social media, you'll see massive, like huge amounts of mixed language content, and this is not an edge case. It's basically the norm. Look at these real user input examples on the left. You have Russian, French, or Hindi mixed with English. And why does this happen? Brand names, they stay in English, and like most of the time, and users, they naturally code switch, and marketing for brands and products is often mixed between languages. So the model impact here is quite significant because it breaks tokenization and it confuses semantic understanding. So let's take a look. In one analysis of Russian e-commerce data, 45% of product queries contains at least one English word, and 23 of product titles were entirely in English, and that's despite being on a Russian website. But there are actually three practical solutions that we can apply. Option one, it's pre-processing normalization. We can detect language mixing and normalize everything to one language. For example, we can make so all variations of iPhone Red with one word in English and one word in Russian, they all become iPhone Red fully English or fully Russian, depending on the model we use. So the upside here is cleaner input for the model, but the downside is you can lose some information, and sometimes transliteration can be ambiguous. Then there's option two, which is data augmentation during training. We can artificially create mixed language examples and train the model to handle both options. For example, for iPhone Red, we have the first word in Russian and the second in English, and vice versa. We can train the model to handle both of these examples. However, this does require more training data and effort, but the model learns to handle real user behavior at the end. And we have the third option, which is language-aware preprocessing. We can tag which parts of text are in which language, process each segment with the appropriate tokenizer, and then combine the presentations. This is more accurate, but also more complex and adds latency. In my opinion, for most applications, option two, which is data augmentation, gives the best balance because it includes mixed language examples in your training data because it's more representative of reality anyway. Now for the code switching. It is when speakers alternate between languages within a single interaction. Unfortunately it's a linguistic reality, and especially in multilingual communities. And if your system serves these communities, you have to be able to handle it. So here on the slides you can see different types of code switching. You have intersentential, when there are different languages between sentences. Then you have intrasentential code switching when the switching happens inside one sentence, and you have tag switching, which is which are quick insertions from another language. But where are those cases most common? Well, immigrant communities, tech-heavy contexts where English technical terms mix with local language, and especially social media where casual mixing is the norm. The performance impact could be quite dramatic. In a sentiment analysis task I ran before the webinar, uh, the clean single the clean single language test achieved 87% accuracy, and the code switch tests from the same domain dropped to 64%, and that's a 23-point drop, which is quite significant. So the best approach, in my opinion, is to start with synthetic code switching in your training data for quicker wins and gains, and then gradually you can collect real code switch data as you scale. Now let's look at encoding. Encoding issues are not the most interesting issues to work on, but they'll silently destroy your model's performance without you even realizing. So you have to look out for that. Um, Let me share a horror story. In one system, from my experience, which I reviewed, there was Russian text which was stored in Windows 12.51 encoding in the database, but the actual application expected UTF-8. Um, so as a result, every Cyrillic character was corrupted. The model trained on this corrupted data achieved only 43% accuracy, which is quite poor. And after fixing the encoding, it was 78 accuracy. So a huge gain, 35 points improvement. So yeah, in that specific case, it was a huge win. Let's look at the comparison table on the right. On the left part of it, you can see properly encoded UTF-8 text, and on the right, you see the same text but corrupted because of encodings. And Russian equivalent of "Hello World" becomes unreadable garbage, and Chinese characters become nonsensical symbols. And for other languages, it's pretty much similar. So common issues include UTF-8 versus legacy encodings, Mojibake, which is corrupted characters. There's also zero width invisible characters, and right to left text handling for Arabic and Hebrew. The impact is that the model sees garbage and can't properly learn the patterns. But there is a straightforward prevention. You can enforce a strict UTF-8. You can make a strict UTF-8 enforcement everywhere in your pipeline. In your database schema, validate on data ingestion, normalize Unicode characters, strip invisible characters, add encoding validation test to your CI/CD pipeline, and that should do the trick. And if you're working with data from multiple sources, user input, web scraping, legacy databases, you should assume that the encoding issues exist until proven otherwise. So you have to take that into consideration. The latency budget reality. In research, we usually optimize for accuracy, but in production, we have to optimize for accuracy within a latency budget, and this changes everything. Look at user expectations for different application. Web search needs to be under 100 milliseconds. Then e-commerce needs to be under 200 milliseconds, generally speaking, and chatbots can tolerate up to 500 milliseconds. Now let's look at typical model inference times on CPU. Ember takes about 30 to 50 milliseconds, XLM-R base version takes 70 to 100 milliseconds, XLM-R large takes 150 to 200 milliseconds, and MT5 large takes 300 to 500 milliseconds. And here's the math that matters. Look at this response time breakdown for a 200 millisecond target in an e-commerce system on the graph on the graph here. Network latency takes about 60 milliseconds round trip. Load balancing, pre-processing, post-processing, database operations, these all add up to another 50 something milliseconds. And that leaves roughly 85 milliseconds for model inference. So if you were to choose XLM-R large at 150 to 200 milliseconds inference, you've already over your budget. And you need to choose a model that fits within your latency constraints, not just your accuracy goals. Have to balance those things together. Uh, and the trade-offs are real. You can't have the most accurate model with the lowest latency at the lowest cost, so you always have to pick two. You optimize for what matters most to your application. Um, Now let's talk money. Here's what monthly costs could look like for system handling 1 million requests per day. Uh, for Embed, and here for hardware, we use the AWS hardware, AWS servers. We have a monthly cost of about $400 per month with latency of 35 milliseconds and accuracy of 84%. Then for XLMR base version, we have monthly cost of $900, latency 80 milliseconds and accuracy 87%. Then XLMR large GPU, we have $1,200 monthly cost, latency of 45 milliseconds and 90% accuracy. And we also have a custom distilled option, which will be cheaper to run at about $300 per month with latency of 25 milliseconds and accuracy of 82%. But do keep in mind that these are just the direct infrastructure costs. There are also hidden costs that include model storage. For example, XLMR large is 2.2 gigabytes, and you don't just store one model. You have like if you version models, multiply that by the number of versions, and that could grow really quick. Then you have data preprocessing pipelines. You have monitoring infrastructure, training and retraining costs, which is GPU time for fine tuning, which can be roughly from $50 to $500 per training run, or even more depending on the model. Then there is also data labeling, which could go from 5 cents to 50 cents per label, and it all adds up. But there is a question that you need to answer to yourself. Does that 6% accuracy improvement from 84 to 90 generate enough additional revenue for your case to justify the extra costs? You'll have to do the math for your specific use case. But when should you actually pay more? High value transactions where each error is expensive. For example, user facing applications where accuracy impacts satisfaction, or safety critical applications. And where could you like save money? These are internal tools where humans can catch errors, some non-critical tasks, and early stage products where you just need to prove value first and then work on accuracy. Now let's talk architecture. You have three main options. Option 1, single multilingual model. User input goes through language detection, then to one multilingual model, like we discussed, like XLMR or Embed, then output. The advantage is the simplicity, one model to deploy, version, and maintain. And adding new languages is easy if zero-shot works. The disadvantage is compromised accuracy because it's jack of all trades and master of none. High resource languages underperform compared to specialized models. Then you have option 2, language specific models. User input goes through language detection, then a router sends it to appropriate language specific model, for example, English bird, Russian bird, Chinese bird, and etc. The advantage is the best possible accuracy for each language, but and you can also optimize each model independently, but the disadvantage is the complexity, because you have n models to train, deploy, monitor, and maintain at the same time, and it doesn't scale well to many languages. And you have a combination of those two approaches, the third option, which is a hybrid approach, which I would actually recommend for most cases. Because user inputs here goes through language detection, then a smart router, and high traffic languages like English, Spanish, and German, they are directed to specialized models, and everything else goes to a multilingual model for the long tail. This way you get the best accuracy where it matters, like with the most traffic, for example, uh, while you also remain scalable to many languages. And there's actually a quite simple decision framework. How many languages you have? If one, two, you should go. You should just go language specific. If 3, 5, or 6, if you have 3 to 5 with similar traffic, then you can consider hybrid, but single multilingual might work. If 6 to 15, definitely go hybrid, and if more than 15, just single multilingual, because it is going to be extremely hard to maintain so many different models. Uh, also, you can also there are accuracy requirements. If you need like high accuracy, for example, 95% or more, you'll have to go language specific because multilingual just won't cut it. Uh, if uh, if your accuracy, if you're fine with 85 to 95, let's say, hybrid should work well. And if even lower accuracy, like 75 plus, is acceptable, then single multilingual would be fine. Also it depends on your team size, because if you have just 1 or 2 engineers, you can't really maintain multiple models. uh, you'd better go with you'd be better off with single multilingual. But if you have 3, 5 engineers, you can try, like, the hybrid approach could be feasible. And if you have 6 or more engineers, like, any option works. You are quite flexible here. Now let's talk monitoring. In monolingual systems, one dashboard is usually enough, but in multilingual systems, you need per language visibility because, for example, if there is a bug which affects Russian users, it might be invisible in aggregate metrics, but it could be invisible in aggregate metrics if it's only 10% of the traffic, but you still have a problem which is invisible on one single dashboard. Let's look at this dashboard example on the slide. At the top, we have overall system health, total requests, average accuracy, average latency, but the critical information is in the per language breakdown. Notice how English shows 89% accuracy, stable at -1% from the baseline. Spanish is similar at 86, but look at Russian, 72% accuracy, which is down 6% from the baseline, and it shows an alert status warning. Then there is also 64% for Thai, which is down 8% from the baseline, status critical, needs attention. And if you only look at the aggregate, you will see that you have 84.2% accuracy, and you might think that everything is fine, everything works as intended, but it's actually not under the hood, because you're missing critical issues affecting specific user populations, and you have to pay attention to that. What metrics to monitor for each language? Well, you could monitor accuracy or F1 score. You should also monitor latency at P50, P95, and P99 percentiles, then error rate and error types, also data distribution drift and language distribution changes. As in regards to what alert thresholds you should set, in general, I would say if accuracy drops greater than 3% sustained for at least several hours, then for latency, I would say if it increases greater than 20% from the baseline, and also try to catch new error patterns that weren't seen before. So you should set up your monitoring in a way so you can learn about issues before your users complain, ideally. Now, how do you know when to retrain versus when to optimize? Well, here's a simple framework. You should retrain when accuracy drops due to drift. For example, your model was trained on 2023 data and now it's 2025. New slang appeared, new product categories emerged, user behavior changed. And the model's accuracy can drop even though nothing really changed in the model itself. You can also retrain when you have persistent poor performance in a specific language. Uh, as for optimization, you should optimize when the model is accurate but too slow, or when infrastructure costs are too high but current accuracy is acceptable for your use case. Techniques could include quantization, which in quantization we convert float 32 weights to integer 8 weights, and we get a 4 times smaller model and 2 to 3 times faster inference with typically only 0.5 to 1% accuracy loss. Then there is also model distillation, which trains a smaller student model to mimic a larger teacher model, reducing parameters by 40 to 60% with only 2 to 3 accuracy loss. Then there is also ONNX runtime conversion, which can give you up to 2 to 3 times speed up with basically no accuracy loss. Collect more data when you see consistent errors in specific categories, or when adding new languages where zero-shot performance isn't acceptable. The key is having the monitoring in place to know which situation you're actually in. Data collection strategy. Let's say you want to support 10 languages. Do you need to label 10,000 examples for each language before you start? That could be from $50,000 to $100,000 in labeling costs. But actually, no, there is a smarter approach. Phase 1, you can start with a zero-shot. Deploy a multilingual model with zero-shot capability trained only in English. Set up logging for all predictions. Add a report error button for users, and monitor which languages have the most errors. For example, after 1 week, you might find that English is 88% accuracy, Spanish 79%, Russian 68%, Thai at 54%. And user errors reports show that Thai accounting for 45% of reports and Russian 30%. And we have the conclusion that we should prioritize Thai and Russian for data collection to enhance the results. And cost for this phase is zero because labeling, well, basically zero for labeling because we just deploy and observe. Then phase 2, targeted collection. We use active learning to find the most informative examples. We focus on languages identified, which we haven't identified in the first phase. We start with say 1,000 to 2,000 examples per priority language, and instead of randomly labeling examples, we select ones where the model is most uncertain. Low confidence predictions near decision boundaries. And this can give you 3 to 5 times more improvement per labeled example. And then phase 3, scale with continuous improvements. We use high confidence model predictions as pseudo labels, and human review only for low confidence predictions. This can reduce labeling costs by 80%, which is pretty good, and also maintain quality. So let's go through the production deployment checklist. So model selection. Have you benchmarked on your data, not just public benchmarks? Have you tested on your infrastructure, not on your infrastructure to verify actual latency? Have you calculated your costs, including hidden costs like retraining, monitoring, etc.? Then data pipeline. Is UTF-8 encoding enforced throughout the whole pipeline? Have you tested the text normalization across all your languages? Is quality monitoring in place to catch issues early? Then for monitoring, do you have per language metrics, not just aggregate? Are alerts configured for accuracy drops, latency increases, and new error patterns? Is error logging ready for debugging? And rollback plan, like can you revert to the previous model version instantly? Is A/B testing ready so you can gradually roll out new models? And are all versions tracked and accessible? And obviously some tips like don't deploy on Friday, don't deploy without rollback capability, and don't deploy without per language monitoring. So let's wrap up with the 6 most important lessons. First, multilingual is not the same as equal. Multilingual does not mean equal because performance varies drastically by language. Because English will almost always be the best, and low resource languages will struggle, and you have to plan for this. Then second, test on your data because research benchmarks they don't reflect production reality in most cases. For example, XLMR achieves 90% on excellent XNLI benchmark, but on your e-commerce data with typos and mixed languages, best case scenario it could be 75%. So always validate on production like data. Then third, you have to know your trade-offs. You can't have the most accurate model with the lowest latency at the lowest cost. Accuracy versus latency versus costs, you have to pick two. Then fourth takeaway, monitor per language. And 85% overall accuracy might sound fine, but if English is 92% and Thai is 58, then you have a problem. You have you might have a case where aggregate metrics hide real critical issues under the hood, which affect real users. Fifth, you should start simple, iterate, and don't try to build the perfect multilingual system on day one. You can just start with zero shot, identify where it fails, then collect targeted data over time and improve. This is way faster and cheaper than labeling 100,000 examples upfront. Then six, engineer for production. The difference between a research project and a production system is all the boring stuff. UTF-8 handling, monitoring, rollback plans, error logging. You don't just don't skip this. Uh, so yeah, multilingual NLP is quite hard. It's harder than monolingual, obviously, and it's harder than the papers make it seem. But it's also doable at the end of the day, and it's incredibly valuable if you do it right. Um, Thank you for your attention. I'd love to hear about your experiences, your questions. What are your biggest challenges? What were the biggest challenges you faced with multilingual models? And yeah, so the Q&A session is open. Feel free to share your questions in the chat. I'll try to answer them. Okay, we have quite a few questions. Let's go one on one. How to handle the situation where language isn't in the original model's training data at all? Like, what if we need to support a very low resource language? Well, this is actually quite quite tough situation, but it's not hopeless. There are a few options. First, you can try the multilingual model anyway, because XLMR was explicitly trained on 100, even I think even more than 100 of languages. But it's seen data from many more through command crawl because only 100 something languages were identified, and there are actually way more languages that were collected through command crawl. And even if your language isn't in the official list, if it shares a script with a supported language, you might get some transfer, some language transfer. Uh, then a language using Cyrillic script will benefit from Russian training data, for example. Just test it, you might get 50-60% accuracy, which could be a usable starting point. Then, secondly, you can also search Hugging Face for language-specific models, because community has lots of pre-trained bird models for many languages that aren't in the big multilingual models, and there's probably already a model for your specific language that someone in that language community has already trained. Uh, Also, if you have access to lots of unlabeled text in that language, like millions of sentences from news, Wikipedia, web scraping, whatever data you have, you can continue pre-training XLMR on the data actually, and this will teach the model the language's patterns before you fine-tune on your task, and it might, well, obviously it will require some compute resources, but much less than training from scratch. And as a last resort, I would say you could train a model from scratch, but honestly, it's only viable if you're like a large company with significant resources, and in most cases, the previous options would suffice, I would say. um, okay, another question we have. Um, I have a couple of questions, if you don't mind. I'm a co-founder of a small startup with just 2 ML engineers. We need to support 8 languages, but we don't have a great budget. Um, well, let me think. Um, well, that's that's a good question, and I would say nowadays it could be a quite common situation. So with such a small team and 8 languages, I think I'd recommend to start with a single XLMR. Uh, I'd say base model. Don't try to build separate models for each language, because you simply won't have the human, like the engineering capacity to maintain them and support them. And XLMR base should give you a good balance of accuracy and reasonable inference speed. So deploy it with the zero shot first. Train on whatever labeled data you have. Um, Even if it's mostly in 1 or 2 languages, the cross-lingual transfer will give you reasonable performance in the other languages to start. Then, also quite crucial, you should set up logging and add a simple feedback mechanism, even just a thumbs up or thumbs down button. Uh, and you should watch which languages get the most negative feedback, and that will tell you where to focus with your limited data collection budget. And after like a month or two, you should have real data showing, for example, that Vietnamese is struggling while Spanish is fine. So then you will know that you can spend your labeling budget on those uh, problematic languages specifically, and maybe start with just 1 or 2 thousand examples each, and you'll get way more, way much, way, you'll get way much more improvement per dollar than trying to label everything equally up front. Also, one more tip: you can use a managed infrastructure like AWS SageMaker or even Hugging Face inference endpoints to start. It is slightly more expensive per request, but you save enormous engineering time on deployment and scaling. And for a small team, that's trade-off could be worth it, I would say. Yeah. Um, Um, and one more question for ongoing monitoring. What's the minimum viable setup you'd recommend? We don't have dedicated ML ops resources. Um, okay. So if you are resource constrained, I think you should focus on these three things. First, you have to log every prediction with the language tag, the confidence score, and ideally, a hash or sample of the input. You don't need like lots of fancy tooling. Even just writing to a structured log file or simple database would work. Um, the key here is having the data to analyze, so you could analyze it later. Then you should set up one dashboard per language accuracy. If you're already using something like Grafana or even just spreadsheet that updates daily, track accuracy by language over time this way. And you don't really need real-time monitoring on day one. You could just have a daily batch job that calculates yesterday metrics, and that's fine. Uh, so here you're looking for trends, so gradual decline over weeks or sudden drops. That would be helpful for you. And a third, I think you should create one alert for significant accuracy drops, something like if any language drops more than, let's say, 5% uh, below its baseline for like 2 days straight for 48 hours, send an email or Slack message. There are lots of ways to automate these things nowadays, for example, like Zap or N8N. Um, this catches both sudden problems like a data pipeline breaking or gradual shift that you might otherwise miss. And yeah, that's it. So structured logging, simple per language dashboard, and one alert rule. And if you can build this in a like couple of days, it should cover 90% of what you need. And everything else, that's just optimization for later, once you've proven the value for of the basic setup, and when you have when you if or when you actually have a proper engineer in place. And yeah, don't let the perfect be the enemy of good, I would say. uh, we have one more question. What is your opinion using LLMs like GPT-4 or Claude on multilingual classification instead of fine-tuning bird models? Is it worth the cost? um, well um, uh, yeah, I mean that's a question that's quite popular these days because honestly, the models like Claude's Opus, Sonnet, or GPT, they even came up like with 5.1 recently. They're quite impressive. Uh, like their performance is their accuracy and how good they are. It's actually insane. But uh, the answer here is it really depends on your scale and requirements, because when the models from Anthropic and OpenAI are genuinely impressive for multilingual tasks, they're very expensive. I mean, they're easy to use. Their performance is good, but they're expensive and they have privacy concerns, because the latency could be like from 500 milliseconds up to even like 2 or more seconds, and that's way worse than 30 to 100 milliseconds from BERT model, which is run locally on your hardware or rented hardware. And that might be fine for chatbot, but it's not acceptable for real-time search, let's say, or high volume classification. And costs for these models scale with volume at 10,000 requests per day. Using an LLM API might cost just huge amounts of money, and which could be saved by using your own models. Um, Also, there's data privacy concerns because you're basically sending customer data to a third-party API, and that's not, in most cases, it's not really acceptable, especially in certain industries. So my recommendation would be to use LLM, to use large language models with APIs just for a couple of things. One, I would say, is rapid prototyping, when you have to validate your idea that it works before investing in proper infrastructure, uh, because it's way easier to quickly set it up. Then it also could be good for data labeling, because you could use something like GPT-5 to generate training labels for your fine-tuned model. And I've done this where we spent just hundreds instead of thousands or tens of thousands of dollars on GPT to label 10,000 examples, and then trained an XLMR model that serves millions of requests per month, and that's just at a tiny fraction of the cost. So it's not like either one. I would say you could use a large language model strategically to bootstrap your traditional ML models. Yeah, I hope that answers your question. Um, thank you. Yeah. One more question. You showed hybrid architecture with specialized models for high traffic languages. How do you actually implement the routing? What if the language detection is wrong? Um, um, mhm. Well, there are actually, I mean, the routing itself is straightforward. You just you run language detection first, which is quite low on resources. I would recommend something like fast text language identifier because, well, obviously it's fast, about just 1 millisecond, and it's quite accurate for text over 50 characters. Then, based on detected language, you route to either your specialized model or your multilingual fallback, depending on your architecture. And I would say what's more tricky here is actually handling detection, like actually handling the error detection, because yeah, that could be tricky. Because wrong detection means wrong model, which can mean terrible results. And there are several strategies. Well, one, you could use confidence thresholds. Like I mentioned, fast text, it returns a confidence score, and you can set that if the confidence below, let's say 80%, then routes to your multilingual model instead of a language specific one. Uh, but well, because the multilingual model can handle mixed or ambiguous input better. Then second, for very short texts, let's say under 20 characters, language detection is quite unreliable for any tool, and for those cases, either use the multilingual model by default or use contextual signals like the user's local setting or the language of the web page they're on. So yeah, you gotta like use other information you have. And also you can monitor your routing decisions and track cases where language specific model returns very low confidence predictions. And this way, like this pattern would probably indicate misrouting. And yeah, in practice, with proper thresholds, misrouting, like in real world, I would say it affects less than 2 or 3% of requests. So uh, since your multilingual fallback model can handle any language reasonably well, I would say even misrouted requests don't completely fail because they just get slightly lower accuracy than optimal, and that's not the end of the world. Yeah, I hope that answers your question. Okay, let's. I can't see any more questions in the chat. Let me know if you have any more questions, and if you are satisfied with my answers to your current questions. Yeah, I'm glad it was. I'm glad it was useful. Also, in the description, I would after the stream is over, I will add a link to my GitHub with code snippets for some of the concepts I touched on here in this talk. So you could actually use some of those or like take a better look at them. And yeah. So yeah, it seems like there are no more questions. Thank you everyone for coming. Uh, and yeah, looking forward to having a second webinar in this series. I will post the details in my LinkedIn, and feel free to reach out if you have any more questions. I'm always open. Thank you and have a great day.